Next we have number 12. There are two parts. Let us see part A first. Here we have to find the general form of all positive integers n for which tau of n is equal to 10. That means for which the number of positive divisors is exactly equal to 10. And we have to also find the smallest positive integer for which this is true. So let's go for the solution. Okay, so the solution starts like this. In the beginning itself, we note that because tau of 1 is equal to 1 and not 10, so our n cannot be 1. It seems like a very simple thing, but because n is not equal to 1, n is greater than 1, and that is why by the fundamental theorem of arithmetic, n has a prime factorization. So let the canonical factorization of n be this, where you already know what these things are, but still we have to write, where the pi's are distinct primes and each exponent ki is a positive integer. So from this factorization, we know what tau of n is in terms of these exponents. We add 1 to each exponent and we take the product of those numbers. That is our tau of n, and that should be equal to 10. Now from this equation, we have to figure out what type of exponents we can possibly have and what will happen to n. What type of number n is. How can we do that? Let's see. So next what we do, next we suppose that r is greater than or equal to 3. What is r? R is this. That means in the original factorization of n, r distinct primes appear, and we are supposing that at least 3 distinct primes are dividing n. That means they are appearing in the factorization of n. Then there exist primes p, q and r, which themselves are not necessarily distinct, such that p divides k1 plus 1, q divides k2 plus 1 and r divides k3 plus 1. Why? Well, if we are assuming that r is at least 3, then we know that at least k1 and k2 and k3 are there. There may be k4, k5, may not be, we don't know, but at least k1, k2 and k3 are there. And what are these k1, k2 and k3? They are positive integers. So they can be at least 1. They cannot be 0 because they are positive integers. And as such, k1 plus 1 is a positive integer greater than 1. And so is k2 plus 1 and so is k3 plus 1. So again, because they are positive integers greater than 1, we can apply the fundamental theorem of arithmetic. Whatever we did with n, now we are doing that with these 3 numbers, k1 plus 1, k2 plus 1 and k3 plus 1 is there. But we are of course not writing factorizations of these numbers. The fact that each one of them is greater than 1 guarantees that each one of them has a prime divisor, and those prime divisors are p, q and r. They may or may not be distinct, we don't know. Maybe this p, q and r, actually all 3 of them are the same prime, that is also possible. But then what do we have? Then from this equation, what do we see? P divides this, and that's why p will divide 10. But simultaneously, you see, they may not be distinct, but the fact is that we do have k1 plus 1, k2 plus 1 and k3 plus 1 on the left hand side of this equation. So k1 plus 1 can be written as p times some integer, k2 plus 1 can be written as q times some integer, and k3 plus 1 will be r times some integer. So you are actually getting p, q, r on the left hand side times something. So that is why p, q, r divides 10. But this is not possible. Why? Well, is it possible for 3 primes to divide 10 in the sense that their product divides 10? 10 already has only two prime divisors, 2 and 5. Okay. So let us look at the different cases. If P, Q and R are all distinct, they are all different primes, then this is not possible because 10 already is 2 times 5. So if P is say 2, Q is 5, then there is no place for R. But if say two of them are equal and the other one is different, but then if two of them are equal, then 10 is divisible by the square of a prime. That is also not possible because 10 is not divisible by the square of any prime. 10 is a square free number. And if all of them are the same, then 10 is divisible by the cube of a prime. That is also not possible. And that's why this is an impossibility. And this impossibility arose from our supposition, which must be hence false. And that is why R cannot be greater than or equal to 3. R has to be less than or equal to 2. You note one thing, that R itself is a positive integer because R is the number of prime factors in the factorization of n. Now this further restriction tells us that R has only two possible values, 1 and 2, and accordingly we can now say something about the number n itself. So accordingly either R is 1 or R is 2. Let us see the one case first. If R is equal to 1, then how does the number n look? There is only one prime factor, p1. That means n is equal to p1 to the power k1. And that equation looks like this, k1 plus 1 equal to 10. In that equation there is only one factor on the left hand side. So from this we are actually getting the value of k1 to be 9. So the number n now looks like this, p1 to the power 9. This is all we can say about it, because this p1 can be any prime. Note carefully that from the formula for the tau function in terms of the exponents in the prime factorization of n, we see that the number of positive divisors of n actually depends only on the exponents, not the primes themselves. So any number of this form will have exactly 10 positive divisors because the tau value of n will be 9 plus 1, that's it. So in this case, this is how n looks. Next, let us consider the case r equal to 2. Here, however, we have two prime factors, p1 and p2. And that equation looks like this here, k1 plus 1 times k2 plus 1 equal to 10. And from this equation and the fact that k1 and k2 are both positive integers, you have only two solutions. And that too, those two solutions essentially are just one solution. Either you have k1 equal to 1 and k2 equal to 4, or you have k1 equal to 4 and k2 equal to 1. If you are finding it a little difficult to see how we are getting this, I suggest you write the right hand side as 2 times 5. Okay. And then you think of the equation. This is a positive integer greater than 1, k1 plus 1, because k1 itself is at least 1. Similarly, k2 plus 1 is also greater than 1. That's the left hand side, and the right hand side is 2 times 5. Okay, and from there, you try to convince yourself using elementary number theory, the things about divisibility that we have seen so far, that these are the only two possibilities. I am not going to say exactly how that happens, okay, I am leaving that to you. So we can assume without loss of generality that k1 is 1 and k2 is 4. And that's why in this case our n looks like this, p1 to the power k1, k1 is 1, so we have simply p1 here, and p2 to the power k2, k2 is 4. You can see why we have chosen only one of these two possibilities, because what will you have in the other possibility? You would have P2 times P1 to the power 4. Because we are not saying which of these two primes is smaller, which one is greater. So essentially we are getting the same type of number in both these cases. So in this case, this is how n looks in general. And then we also have to say what is the smallest positive integer whose tau value is 10. So now we know that our n looks either like this or like this. Now in order to have the smallest n, what value of P1 will you take here? The smallest prime 2. 2 to the power 9, however, turns out to be greater than the other possibilities that we have from this case. In this case also we want to choose P1 and P2 as small as we can, keeping in mind, however, that they are distinct primes. So you have only two choices now. Either you choose P1 equal to 2 and P2 equal to 3, or you choose P1 equal to 3 and P2 equal to 2. If you take 3 here, 3 to the power 4 is 81. 81, already you are getting 81, and that you will multiply by 2, you will get a bigger number. Instead, if you take P1 equal to 3 and P2 equal to 2, then here you are getting 48, 3 times 16. So among all the possibilities that we get from these two cases, this is the smallest. So 48 is the smallest positive integer whose number of divisors is exactly 10. So this is part A. Next, let's see part B. So this is part B. Show that there is no positive integer n satisfying sigma of n equal to 10. It's a bit strange that no n has sigma value equal to 10. Sum of positive divisors is never 10 for any integer n. So let's solve it. In proving this type of claims, where we are told to prove that a certain thing is not possible, we suppose that it is possible, and then we try to arrive at a contradiction. So here also, suppose sigma of n is equal to 10 for some positive integer n. Then you recall, you go back and see the statement of exercise 10 part C. There we proved that if n is a composite integer, then sigma of n is greater than n plus root n. Do you remember? So how can we use that here? If this n is composite, then sigma of n is greater than n plus root n, square root of n. So obviously sigma of n is greater than n, but what if n is prime? If n is prime, then we know that sigma of n is equal to n plus 1. Because what is sigma of n? Sigma of n is the number of, sum of positive divisors of n. And because n is prime, so there are only two positive divisors of n, 1 and n itself. So their sum is n plus 1. So in this case, sigma of n is n plus 1 and still it's greater than n. So in general, we have this inequality. And the supposition that this is equal to 10 now gives us the condition, this restriction on n, that n has to be less than 10. So now we just have to look at the sigma values of the first 9 positive integers, and that we do. Sigma of 1 is 1, sigma of 2 is 3, sigma of 3 is 4, sigma of 4 is 7, sigma of 5 is 6, the next value is 12, then 8, 15, 13. Nowhere do we see 10, and that is why our supposition is wrong. And that's the solution. And let me just end the video here itself. We will solve more exercises next week on the same day. So see you next week. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.